In this video, I will compare solids, liquids, and gases. Let's first watch this animation of the three different states or phases. You are looking at gas, liquid, and solid. This piece of solid has a periodic crystalline structure here.
The states of matter are gas, liquid, and solid. Gases assume the shape and volume of their container. Particles of a gas are separated from each other, move in straight lines, and in a completely random manner. They change direction only when they collide with each other or the container. Liquids have a definite volume and assume the shape of their containers. The particles of a liquid are closely spaced, and so their motion is still random but much more limited. The particles slip past and collide with near neighbors. Solids have a definite shape and volume. Particles of solids are in fixed positions and collide only with near neighbors.
Let's get back to this document. In this table, I will compare solids, liquids, and gases qualitatively. First, the shape. Only solids have a definite shape. Now, volume. Both solids and liquids have a definite volume. Gases do not. Density. Both solids and liquids have a much higher density than gases. Molar volume. The volume of 1 mole solid or liquid is much smaller than the volume of 1 mole gas. Intermolecular net attraction. Molecules attract and repel each other at the same time. This is because if we're looking at two helium atoms, the nucleus of one helium atom repels the nucleus of the other helium atom. But at the same time, the electrons attract the two nuclei. Therefore, both attraction and repulsion are existing between two helium atoms or any other molecules or atoms. Usually, the attraction is greater than the repulsion. The overall between gas, liquid, or solid molecules, there is a net attraction. However, the net attraction in the gas phase is very weak. It's almost negligible because the distance between gas particles is much greater than the distance in between molecules in the liquid or solid phase. So what about the solid and liquid phases? The intermolecular net attraction is much stronger than that in the gas phase. How about the kinetic energy? Kinetic energy depends on the motion. And from the animation, you can see the gas particles move more freely and have higher kinetic energy. In the liquid phase, the molecules can still move around more dramatically than the solid phase. We say the kinetic energy is medium in the liquid phase. How about solid state? The molecules and atoms can still vibrate in the solid state, but not as much as the liquid state. Therefore, the kinetic energy in the solid state or solid phase is the lowest. Now let's compare the solid, liquid, and gas states with one more specific example: water. So let's look at ice at 0 degrees Celsius, liquid water at the room temperature of 25 degrees Celsius, and water vapor, that's water in the gas phase, also at 25 degrees Celsius. Let's look at their density values. The density of ice is roughly 0.9 gram per milliliter. The density of liquid water is a little higher, it's 1.0. How about the density of water molecules in the gas phase? This is much, much smaller than that in the solid or liquid phase. I want you to pay attention to these numbers. Water is very special. In nature, only water has a higher liquid density than the solid density. Now, molar volume. The molar volume of ice and liquid water is roughly 20 or 18 milliliter per mole respectively. What about water vapor in the gas phase? 25 liters. 1 liter is 1,000 milliliters. Therefore, the molar volume of water vapor is at least 1,000 times greater than that of liquid or solid. What about this intermolecular net attraction between water molecules in the solid phase? It's roughly negative 42 kJ per mole. Liquid, negative 37. This is because in the liquid phase, water molecules move around more freely than the solid phase. So it's more difficult to form a perfect hydrogen bonding between two neighboring water molecules. What about the gas phase? This number is so small, it's often neglected. Kinetic energy. In the solid phase, the water molecules can only vibrate more locally. For example, the vibration of the OH bonds in water molecules. In the liquid phase, it's possible for a water molecule to rotate. It's called hindered rotation because of the attraction between the surrounding water molecules and the rotating water molecule. But still, because of this partial rotation or hindered rotation, still the kinetic energy of liquid water molecule is higher than the kinetic energy of solid water molecule. What about the gas phase? You watched the animation and you can see in the gas phase water molecules can translate freely. They move around at several hundred meters per second. Because of this additional translation motion, the kinetic energy of water molecules in the gas phase is greater than that in the liquid phase. These three numbers are not quite different from each other, but remember the kinetic energy of water molecules in the solid state or solid phase is smaller than that in the liquid phase than the gas phase. Now I want to show you a couple pictures of the crystalline structure of ice. Let's look at this picture first. This is one water molecule, and we have oxygen here, two hydrogen atoms. Between the hydrogen and oxygen, there's a chemical bond with a 500 kilojoule per mole bond strength. So this is a very strong bond. Between two neighboring water molecules, for example, between these two, there's a so-called hydrogen bond. The dashed line here is a hydrogen bond. Oxygen is partially negatively charged. Hydrogen is partially positively charged. Therefore, there is an attraction between this hydrogen and this oxygen. Same here, between this oxygen and this hydrogen. Between this hydrogen and this oxygen. And the distance between this hydrogen and this oxygen is roughly 2 angstroms. The distance between this hydrogen and this oxygen with a real chemical bond is roughly 1 angstrom. So you can see between this oxygen and this oxygen, the distance is roughly 3 angstroms, including 1 angstrom here and 2 angstroms here. What about this picture? It's also the crystalline structure of ice. These two are essentially the same structure. But over here, the gray sticks are used to present the hydrogen bond or hydrogen bonding. Now let's work on one example problem here. Given the data provided in the previous page, estimate the change of the internal energy of water in a vaporization process. In the vaporization process, liquid water is converted to water vapor. The initial state is liquid state. The final state is gas state. So what we need to do is we need to use the internal energy of the final state minus the internal energy of the initial state. And also we know that the internal energy is the sum of potential energy and kinetic energy. Therefore, the change of the internal energy is the change of the sum of the potential and kinetic energies. And therefore, it's the sum of the change in potential energy and the change in kinetic energy. What's the change of potential energy? On the previous page, you can see it changes from negative 37 to roughly 0 here. We use the final state, 0, minus the initial state, negative 37. The change is positive 37. How about kinetic energy? The initial value is 14. The final value is 18. What's the change? Final minus initial. The result is 4. Therefore, the kinetic change is 4 kilojoule per mole. Now we have the change in potential energy, which is 37. The change in kinetic energy is 4. What's the total change of the internal energy? Well, that's just 37 plus 4. 41 kilojoule per mole is the result. Let's look at another example problem. Given the density of ice, estimate its molar volume and estimate the average distance between water molecules in ice. Or let's say between two neighboring water molecules in ice. We know 1 mole of ice weighs 18 grams. Given this density, we know 18 grams divided by density is 20 milliliters. That's the volume of 1 mole ice. Therefore, the molar volume is 20 milliliters per mole, or 2 times 10 to the power of negative 5 cubic meter. This is because 1 milliliter is 10 to the power of negative 3 liter, and 1 liter is 10 to the power of negative 3 cubic meter. Therefore, 1 milliliter is 10 to the power of negative 6 cubic meter, and 1 cubic meter is 1 million milliliters. Therefore, we can convert this 20 milliliter per mole to 2 times 10 to the power of negative 5 cubic meter per mole. On average, each water molecule occupies a very, very small space. This is because we need to have this volume for 1 mole water molecules divided by the number of water molecules. The number of water molecules is 6 times 10 to the power of 23. So after we do this division, we get the average volume or average space occupied by 1 water molecule. It's a very small number. It's 3.3 times 10 to the power of negative 29 cubic meter. Now we'll have to imagine dividing the total volume, this 20 milliliters, into 6 times 10 to the power of 23 small cubes. And in each cube, there's a water molecule. and this water molecule sits at the center of the cube. And then we can compute the side length of each of the small cubes. That's the volume of the cube to the power of 1/3. The result is 3.2 times 10 to the power of negative 10 meters, or 3.2 angstroms. This is because 1 angstrom is 10 to the power of negative 10 meters. And also 1 angstrom is equal to 0.1 nanometers. Now we know the side length of the cube is 3.2 angstroms. This is also the average distance between two neighboring water molecules. Again, just imagine, put two cubes next to each other. The distance between the two centers of these two cubes is the side length of the cube. Now I will let you work on two practice problems. The first one is easier. Given the density of liquid water, calculate its molar volume and then convert it to the SI unit. The second one is more difficult. At the boiling point of water under 1 atm pressure, calculate the density of water vapor and estimate the average distance between water molecules. How do we do this? Again, what you need to do is you need to compute the molar volume of water vapor using the ideal gas equation, PV equals RT. Since PV equals RT, the molar volume is V over N, and V over N is equal to RT over P. What's the temperature? 373 Kelvin. What's the pressure? Well, 101,325 pascals. Remember, if you keep using SI units in all steps, the result will also be in the SI unit. So what you need to do is, again, you use RT over P, 8.3 joule per mole K, that's R, 373 in Kelvin, divided by 101,325. The result is in cubic meter per mole. And then what you need to do is you divide the molar volume by Avogadro constant. You will get the average space for each water molecule in the gas phase. That number to the power of 1/3 will give you the average distance between water molecules in the gas phase. And then that number you will see is much longer than the distance between water molecules in the solid phase or liquid phase. That explains the very weak interaction between these water molecules in the gas phase.